Okay. Hello. Okay, I think it's time to start. And yeah, we finished our midterm explanation, and now let's go back to our next part of our course. That's linear transformation. So we talked briefly about linear transformation last Wednesday, and let's start with reviewing a definition. So definition of a linear transformation. Linear transformation. Now we are thinking about mapping between two vector space, where vector space V and vector space W, and mapping between them is a linear transformation if this mapping respects the linearity of the two vector space. Means that if you map a linear combination of two vectors inside V, then the result will be the linear combination of the corresponding vectors inside W. So you have this alpha V1 plus beta V2, you map them, and it becomes alpha of this mapping of V1, so L of V1, plus beta times the mapping of V2, L of V2. Okay, and yeah, this should be true for every V1, V2, and alpha, beta. Okay, so we want this mapping to be to keep the linearity of the vector you are mapping. Okay. And also a bit of a spoiler, we'll see in 4.2 that any such mapping you can represent as matrices. Okay. And yeah, so here is just you can write this linear transformation property either in this way, so just one sentence, or you can break the linear combination into two parts. You can say the mapping respect the addition and respect the scalar multiplication. You can check either these two, or you can just check this one. They are equivalent. Okay, and once again, BM notation. So in mathematics, whenever you have a mapping, you write like this. You write a semicolon. You have your mapping here, and then you write a column, and then then you write the in space and out space, and with the arrow your middle. So this is from the space V to space W. Then it's a V and the arrow and the W. Okay, and then extra notation. So if the starting space and the end space of your mapping is the same, then the mapping is called a linear operator. Okay, so you map yourself, and then we see a whole bunch of linear linear transformation in R2. So if you increase the length of your vector by 3, this is linear. And if you project your vector onto an axis, then this is linear. And if you reflect your vector around an axis, this is linear. And also if you rotate your vector, this is linear. Okay. And all those are linear operation on R2, so you map from R2 vector to R2 vector. And then we also see less geometric example. So we have a linear transformation, say mapping from R2 to R1. That is, you get a linear combination between two of the coordinate of your R2 vector. Then this is also linear. And then we see something that's not linear. That is, you calculate the length of your vector. So this is a mapping from yeah, so this is also R2 to R1. So you map your vector to the length of your vector. So and this is non-linear, and in fact it's not even doesn't even keep the scalar multiplication, because the length of your vector is always positive. So if you multiply your vector by a negative number, then your length don't get multiplied by the same negative number. So this is another linear transformation. And finally, we see we can go from R2 to R3 by going to this by having every coordinate of your R3 vector as a linear combination of your R2 vector. So you can have start with x1, x2, then you go to this x2, x1, x1 plus x2, And now we start to see that how we get a matrix form of our linear transformation. So in this example, we can write this R3 vector as a matrix times our R2 vector. Okay? So we have a matrix of this 0, 1, 1, 0, 1, 1. And if you have this matrix multiplying our R2 vector x1, x2, then you see that this is exactly the R3 vector that is the output state, the output vector. So 0, 1, x1, x2, then become x2, and 1, 0, x1, x2 become x1, and 1, 1 interpolate with x1, x2 become x1 plus x2, etc. Okay. So you see that if every coordinate is a linear combination of the input vector, then you can quite intuitively write down a matrix that such that your output vector is your matrix A times your input vector X. Okay, and yeah, and this can be even proven more general. So yeah, we will do more rigorous proof in chapter in the next section. But for now, we just state this as a theorem. So yeah, so if we have n by n matrix, we can define a linear transformation. So this is two-way. Okay, so we here the statement are two ways, and let me try to find where I didn't. Oh, excuse me. Let me try to get my drawing template. Oh, it's here. Okay. Yeah. Yeah, so here the statement two-way. The first statement here says that if you have a matrix, then you can get a linear transformation. And this is quite obvious. So if you multiply a matrix on your vector, then the outcome will be really linear because matrix multiplication is linear. Okay. Okay, so whenever you multiply your matrix on your vector, this give you a new vector, and this transformation is linear. This just comes from matrix multiplication properties, and it's linear. And the interesting part is you can think about this in reverse. So whenever you can, maybe let's write it here. This here is okay. Okay. So whenever you have a linear transformation between two space, here we say on Euclidean space, so from Rn to Rm, then you can also define a matrix, get a matrix like this way. So you can, from any linear transformation, you can get a matrix that corresponds to this linear transformation, and this will say if you want to do this linear transformation, you can just multiply this matrix on your input vector. Okay. Yeah. So really, there is a one-to-one correspondence between matrix and linear transformation. Okay. And yeah. So later on, we'll 4.2 will prove this. Okay. This is a nice thing to keep in mind, but for now, let's talk about something else. So let's prove some. Okay, so this is about Rn and Rm, and let's talk a little more about linear transformation on abstract spaces. Okay, okay, and yeah. So here are some simple property we can prove on linear transformation of abstract space, and it doesn't have any title in a textbook, but we give it H1 name, so it's easier to say who it is. So we call this theorem 4.1.0. Okay, and there are three properties. So basically, we have some property about the zero and the inverse, and some linear combination. Okay, okay, and so first property says that. Okay, so if you have a linear transformation apply on the zero of the input space, then that will give you the zero of the output space. Okay, and then we have another property says that for any vector inside your input space, you have a linear transformation of the inverse of your vector. then what you get is the inverse of the output vector. Okay. So basically, the getting 0 and the taking inverse respect the linear transformation will get preserved by the linear transformation. And then the second property is quite trivial. It's basically just the linear transformation respect respect a linear combination, but the only difference between this and the definition is that now we have more vectors. So in the definition, we just have a linear combination of 2 vectors. Now we have n vector. Okay. So yeah, so proof, let's start with the easiest one. So the second one is really just by induction. So if your linear transformation respect the linearity between 2 vectors, then you can just add more and more vector to this list. And by induction, this will equal to this linear combination of the outcomes. Okay, so this is really simple, so let's skip this. And then 1 and 3 is a bit harder. Then we need to remember that we have this theorem 3.1.1, which says that if you have 0 scalar multiply on your matrix, 0 scalar multiply on your vector, you get the 0 vector. And also -1 multiply on your vector, you get a minus vector. Okay, and yeah, now you can go from the 0 on space V to 0 on space W by just saying 0 on space V is 0 multiplying on your vector, and then this 0 can get outside of your mapping, because by our definition of a linear transformation, you transform some 0 multiply on something is 0 multiply on your linear transformation. Okay. So the first equality here, we go by theorem 3.1.1, and the second equality, we go by the definition of a linear transformation. And then once again, we use the theorem 3.1.1 on the space of W. So now this L of 0 of V is some vector in W. We don't care about who it is, but it's getting multiplied by scalar 0. So it's the 0 vector inside space W. Okay. So here is the proof. So, and the smart part is you use theorem 3.1.1 and get extra scalar multiplication of 0 here. And then the scalar multiplication can get out of this mapping by L. And then the inverse is a similar thing. So instead of multiplying by 0, you just multiply by -1, and you do the same thing. Then you see that you map the inverse of V is getting the inverse of map of V. Okay. So basically, you can reverse the ordering of doing mapping or doing inverse. Okay. That's because you basically can reverse the ordering of multiplying a scalar and doing the mapping. Okay, that's a linear transformation. Okay, and yeah, so this is a basic property about linear transformation. And now we, okay, so we have a beam extra. Okay, and here we have basic mode definition. So now we go back to linear operator. So we think about yeah, we can define this operator that's linear operator for any space that we can have this operator that just map every vector to itself. Okay, so obviously this mapping from your vector space V back to your vector space V, and it's easy to prove that this is linear. So you have a linear combination, and you apply identity on it, obviously back to the same linear combination, and yeah, you respect the linear combination. Okay. And yeah, so we have a really short proof here, says that the identity operator is also a linear operator. And here this is more about notation here. So we have the notation of identity operator being this big I with a really weird font here. Okay. And you can feel that it's written as big I because it's similar to it's going to be correspond to the identity matrix. Okay. So if you remember, you have identity matrix multiply on any vector back to your same vector. So this identity operator is basically an identity matrix, but it's written in a different font to denote that it's abstract symbol. So this is not totally a matrix. We think it as an abstract mapping from one abstract vector to another abstract vector. Okay. But well, functionality wise, it will be same as multiplying identity matrix. If you can express this vector as Rn vector. Okay. Yeah. So that's the identity operator. And let's go to the the main part of this lecture. That's the imagery of kernel. Okay, so yeah, this is a little bit more about mapping to zero of a linear map. Okay, so let's first talking about the idea of kernel. Okay. So now we have a linear mapping L that map from some vector space V to vector space W. Okay. And what is the mapping? And something will get mapped to 0 of W. I guess the existence we prove here. So we see that 0 of V will get mapped to 0 of W. Okay. So something will get mapped to 0 of W. And but there are other things other than 0 of V that might get to map to 0 of W. And all of them, we call it this set that get mapped to 0 W. We call it kernel of L. Okay. It's called kernel, and it's denoted by this notation kernel of L. Okay. And yeah, mathematical definition is here. Kernel of L is every vector inside V that will get mapped to 0 W. And another way to say this is that this is the pre-image of 0 of W. Okay, pre-image of 0 of W. Okay, and yeah, so this is really a definition, and I guess a bit of a spoiler. We are going to show very soon that this kernel of L for every L being a linear transformation is subspace of V. Okay, and yeah, so this kernel is an important concept. It will tell us a lot about this mapping. Okay, so if this mapping has a larger kernel, then well, you know it has a many to one. It's a many to one mapping, etc. Okay, and yeah, so this is the definition of kernel, and there is also two more subspace that that we want to define, and there are image and range. Okay? And the image and range are now subspace inside W. And what's image? Image need to define with another information, so it's not just defined by V, L, and W. So image is well, it's an image from some subspace from L. Okay, so we have some subspace S. Sorry, some subspace inside V. So we have whatever subspace S of V, and then we can define image of S, and it's just whatever thing that from S get made by L. Okay, and well, yeah, that's pretty intuitive. That's image of this subspace of V. And yeah, so L of S is everything inside W that get made from S to get made from S by L. So V is from S and they get made by L, and all those things together as a set is called the image of image of S. And well, we don't write and for notation. I guess we don't write the image of S as img of S. We just write it's L of S because it's whatever inside S gets made by L. Yeah. So it's I guess slightly different notation from the kernel. Kernel has this curl here, but image is just L of S because this is quite intuitive. And yeah, so imagery of S is like this, and there's a special image of in this mapping that's the image of everything. Okay, so image of everything is L of V, and it has a special name. It's called range of L. So range is the largest possible image. It's the image of inside everything inside V. Okay. And yeah, so those are the three important concepts in this section. We have kernel and image and range. Kernel is a pre-image of 0, and the image is image of whatever subspace you have. And yeah, for simplicity, let's assume that S is always a subspace. And then the image of everything is called range. Okay. So for now, it's just definition, and I think the definition should be intuitive, but obviously you need to memorize those three names. So kernel and image and range. Okay. And yeah, then finally we can prove our theorem that we keep saying. So kernel is going to be a subspace. So for any linear transformation, any space V and any space W, kernel is going to be a subspace, and also S is any subspace of V, and every image is a subspace. Okay, and kernel is a subspace of V, and the image is a subspace of W. Okay, and yeah, let's go through proof. Proof is quite straightforward. So to prove a subspace, basically we need to prove a closure. So we need to prove a closure under scalar multiplication and closure with respect to vector addition. Okay. And yeah, so we have something inside kernel, and we say that it will get mapped to 0. And let's see what will happen if we have alpha times yeah, we have alpha times our vector. Then it will be then it can map to alpha times LOV, and the LOV is 0 inside W, so this is alpha times 0 of W. And this is equal to 0 of W is a homework problem, but I think it's not in problem set, so let's prove this really quick. So then once again we can use our theorem 3.1.1. Okay, so this thing, so we can pull our HR0 to get multiplication. So this is alpha times 0 times 0 of W, and alpha times 0, now this is scalar multiplication, and this is equal to 0 times 0 of W, and that's equal to 0 of W. Okay. And yeah, so this is C1, and so we see any alpha times UV still mapped to 0 of W, so alpha V is inside kernel. And yeah, similarly we have V1 and V2 both mapped to 0 of W. Then you map V1 plus V2, then you have this mapping of V1 plus mapping of V2 by linearity. Then this is 0 of W plus 0 of W, and that's still 0 of W. So yeah, so V1 plus V2 still inside kernel, and yeah, so we see kernel is a subspace of V, okay, because it's closed under scalar multiplication and addition. Okay, and similarly, let's see the image part of the proof. So if there's something inside image, then by definition there is some V that's pre-image of W. So some V inside S that will get mapped to W. And let's think about some alpha times W, and yeah, so something that whether alpha times W is something mapped from something inside S. Well, alpha times W is mapped from, so by now we go the other way of linearity. So alpha times W is mapped from alpha times V by linearity, and but S is a subspace, so alpha times V is a subspace. So we see that, and then we have the similar C for addition. So here we have this W1 and W2, and the W1 plus W2 is made from this V1 plus V2. So basically the closure the closure property of S will translate to the closure property of its image, okay, of the image L of S. Okay, so yeah, so we have alpha V will also inside S. This go to will mean alpha W will be inside of S, and V1 plus V2 inside S will go to W plus 1 W2 will be inside L of S. Okay. And anyway, we prove that L of S is also a subspace because it's closed under scalar multiplication and vector addition. Okay. And yeah, let's see some example to get a bit of intuition about those kernel and image. And let's start with the example that we kind of already see. So we have a linear operator that made from R2 to R2. And it's a projection onto x-axis. So L of x is x1 and 0. So you kill all the second coordinate. You map your vector onto the x-axis. Yeah. And we can solve for what is inside kernel. So something inside kernel, if L of x equal to 0 vector, which in R2 equal to this 0, 0. Okay. And L of x, so for general x1, x2 equal to x1, 0. And this gives us that the x1 must equal to 0 for L of x equal to this 0, 0 vector, which is origin. Okay. And geometrically, we can see that this kernel of x is everything on this y-axis. So the coordinate of x1 equals 0, and you have this y1. Okay. And yeah, to write down this in more algebraic expression, then yeah, kernel of L is 0 on first coordinate and whatever x2 on second coordinate. And yeah, and we can write this as a linear combination of basis elements. So this is x2 times 0, 1, or x2 times the E2 standard vector. Yeah. And so we see this kernel of L is a subspace that's spanned by this E2 vector. So this is a one-dimensional subspace spanned by E2. Yeah. And yeah, so this is kernel. Okay. And then we didn't prove this, but it's pretty easy to see. So range of L, well, range of L is always returning this x1 0 form. So range of L is a one-dimensional space that's spanned by E1. So range of L is this every vector on this x-axis. Okay. So we see that kernel is a subspace spanned by E2, and range is also a subspace. It's a subspace spanned by this E1. Okay. So here are kernel and range. Okay. And let's see more example. We have this R3 to R2 transformation that has every coordinate of this R2 is a linear combination of things inside R3. So its first coordinate is x1 plus x2, second coordinate is x2 plus x3. And yeah, you can write this in matrix form. If you try to write L of x as ax, then A will look like this. So you have 1, 1, 0 for this x1 plus x2, and 0, 1, 1 for this x2 plus x3. Okay, and anyway, now we can solve for kernel and image. Yeah, and kernel is you want x1 plus x2 equal to 0, and x2 plus x3 equal to 0. Okay. And you can set x2. You can set kind of whatever free variable here. Yeah. So basically we solve for this thing. So your ax equal to 0, and we know how to find the solution space of ax equal to 0. This is you try to find the null space of this A here, and where A here is already in the REF, so it's quite easy to solve. We can set x3 as free variable and solve everything. So x3 equal to whatever alpha, then x3 equal to whatever A, then x2 will be minus A, and then x1 will equal to A. And so our kernel will be this A minus A vector for every A, or A times this 1 minus 1 vector. Okay, so kernel of L is a one-dimensional subspace, and here because we treat a little bit right on the matrix form, we also see kernel will be the null space of this matrix here. Okay, so this is I guess theorem we'll see later, and yeah, if you write your linear transformation, if you write the linear transformation as a matrix, then kernel of L will be equal to the null space of A sub L. It's quite easy to see. Okay, and yeah, so this is the kernel. And we also have yeah, and we also want the range of this thing. It's quite easy to see that range is actually everything, and to see range of everything, we need to show well, everything can be written as an image of this mapping, and then we just set arbitrarily. We just have our input vector. Input vector being some A0 B thing. Okay, so we have a lot of middle thing that's I think not important. And yeah, so let's write a parenthesis here. Let's just assume our x equal to this A0B vector, and for whatever a and b, then L of x being this a plus 0 and a plus 0 and 0 plus b, because x1 plus x2 and x2 plus x3, and this is just whatever ab vector inside R2. Okay, so you see that any vector ab inside R2 can be met from this A0B vector in R3, and yeah, so everything inside R2 has a pre-image, so the entire R2 is the range of L. Okay, so that's range of this mapping. Okay, and yeah. And I guess in terms of our a little bit of cheating here, so range will be the result of A times X, and so from so we can also spoil a little bit. So if our L of X equal to A times X, then you will see range of L. So L over V will equal to just the column space. So L, I should write like here, L from V to W. And if your L of x equal to AX, then L is just the column space of A, because it's all the possible linear combination of columns of A. Okay. So yeah, spoiler a little bit. The range will be the column space, and the kernel will be the null space. Okay, but yeah, that's a bit of a spoiler. We can try to remember them later. For now, we finish our chapter 4.1, and yeah, so checklist for point 1. So we define linear transformation. Is the transformation that respect linearity. You have basically the transformation will commute with taking linear combination. So let's write it once again here. L of alpha v plus beta w equal to alpha L of v plus beta L of w. Okay. So doing linear combination first, and do transformation equal to doing transformation first, then doing linear combination. Okay, and yeah, then we have our theorem 4.1.0 saying that 0 and the inverse also commute with linear transformation. So mapping of 0 is 0 in the resulting space, and mapping of inverse is the inverse of mapping. And then yeah, we have a definition of a kernel image in the range here. We have all the picture here. So kernel is a pure image of 0, and well, image is image of whatever subspace here, and range is the image of everything. Okay. And it's important to remember that kernel and the image are subspaces. Okay. And the image are subspace because we restrict this S to be also subspace. Okay. Any questions so far? So this is a 4.1, and I think we are a little bit tight on schedule, so let's try to start 4.2 a little bit. Okay. So 4.2, we want to say, well, now every linear transformation we want to represent them as matrices. Okay, and yeah, we have n by n matrix. Every n by n matrix, we can define a linear transformation as we just said today. By just this L of A is x on x is just A times x. And if matrix is n by n, this will be a mapping from Rn to Rn, because x will be n-dimensional vector, and Ax will be an m-dimensional vector. Okay, and yeah, and yeah, now we want to prove this theorem, saying that whenever we have a linear transformation from Rn to Rn, then we can also find a matrix that corresponds to this linear transformation. And this L of x equal to A sub L of x. Yeah. And yeah, I think we can probably prove this theorem and call it a day. Okay. And yeah, so let's try to find this matrix Al. So if we have whatever linear transformation L from Rn to Rn, how we find the matrix Al? That will, if you just multiply this matrix on X, will give us this linear transformation. Okay. And and yeah, we have a very constructive proof here. We not only say that this A sub L exists. Oh, here this should be A sub L. So not only this A sub L exists, and I guess we are being lazy here. Yeah, we're being lazy. We miss all the sub L here. So so A equal to A sub L. So let's be a little lazy here. And yeah, so we have a very constructive proof of here. We told us how to find this A. So we can find every column of A by just map the standard basis vectors of Rn by L. Okay. So the jth column of A will be mapping of the jth standard vector from Rn. Will be the mapping of this EJ, mapping of the jth standard vector. Okay. And remember this AJ is this notation. So this matrix A is written is this collection of column vectors. So matrix A is written as this A1 vector, A2 vector, A3 vector, etc. to AN vector. And also EJ is the standard vector. So it's a vector where it's all 0 and only have the 1 on the jth element. Okay. And yeah, so this is our construction of A, and we want to see that this will work out. Okay. And yeah, let's see the proof. So what's A times X? So A times X is this matrix is written out as a matrix. Matrix elements is like this. So we have all those elements of A. So A11, A21, AN1, etc. And times the X vector X1, X2 to Xn. Yeah. And we say we define the columns of A as these both face A vectors. So AJ. So we have A1, A2, etc. here. Okay. And we define them as L of EJ. Okay. And we want to see this AX will give us L of x. Okay, and yeah, so a whole bunch of notation. A equal to this collection of column vectors, and yeah. Anyway, so let's see this workout, and this is really just seeing matrix multiplication as a linear combination of column vector, as we see multiple times. Okay, so x can be written as a linear combination of those standard basis elements. So x equal to x1 e1 plus x2 e2 plus all the way to xn en, obviously. And yeah, and then L of x will equal to L of well, this linear combination of standard basis, and then on the second line we use linearity. The L of x should equal to x1 L of e1 plus x2 L of e2 all the way to plus xn L of en. This is by linearity. Okay, so here we use abstract linearity of our arrow mapping. You have a linear combination of standard basis, then you have a linear combination of the mapping of standard basis. Okay. And then also by our definition, L of E1 should be equal to A1, and L of E2 should equal to A2, and L of En should equal to An, etc. Because that's how we define our A1, A2 to An. And yeah, then then we write down this in kind of a matrix form. We see that we have this linear combination of a column vector, and it's so yeah, and this thing can basically jump to here. Then we can interpret our matrix multiplication as a linear combination of column vector, as we told in chapter 1. So basically we can jump from here to here from chapter 1. We say linear combination matrix multiplication by on a vector is a linear combination of the column vector. Okay. And we can see this once again here. So you have all those column vector multiply this x1, x2, xn vector, and it will be a linear combination of them. You can just write by the matrix multiplication rule. Okay, so yeah, so this is the proof. So so this is a proof whenever you have a linear combination, linear transformation between Euclidean spaces, so some Rn to some Rn, then that linear transformation can be always written as a matrix, and the transformation is just multiplying your matrix on the input vector. So yeah, matrix multiplication is very useful because you can represent any linear transformation. Okay, and yeah, once again, this is a conclusion of our linear transformation. So our A is this collection of mapping of the standard basis element. So A1 is the mapping of E1, A2 is the mapping of E2, etc. Our first column is the mapping of E1, and the second column is mapping of E2, etc. And we have an extra name for this A. A is called standard matrix representation of L. And I guess we can talk about a little bit about like this naming scheme of abstract algebra. Okay, so so we have this name representation. So what does representation mean? Is actually something very simple, but it's the idea that people do a lot in algebra. That is, whenever you have abstract you have abstract mathematical concept or abstract algebraic concept, and you write it as a matrix, then it's called a representation. Okay, so a representation just means writing abstract concept as a matrix. Okay, abstract concept as a matrix, and usually it's a linear concept. So yeah, I think well, it's a bit tricky, but yeah, sometimes it's not really linear. Yeah, so I guess it's not every time it's linear. But yeah, representation just means writing down your thing as a matrix, and it's a bit of a side note. And anyway, this is a standard representation of L because this is the most straightforward thing you can think about how to write L as a matrix. Yeah, and yeah, let's 5 minutes. I guess you can see some example of this representation of L, and I guess we already cheated a little bit. We already write down the representation of this mapping, but well, we can see how to do this in a slower way. So we have this mapping from R3 to R2, where the result is x1 plus x2 on first coordinate and x2 plus x3 on the second coordinate. Okay, and yeah, then we can find the 3 columns of this L by mapping the standard basis 3 standard basis element. So we map 1 0 0 0 1 0 and 0 0 1. Okay, and we see A1 by L of E1 is 1 1 0 here. Then you have 1 plus 0 and 0 plus 0 here, and this is a 1 0 vector. And you map E2, then you see the 0 plus 1 1 plus 0 it's a 1 1, and then you map E3 is 0 0 plus and 0 1 is 0 1. So we have A1, A2, A3 here, and it's 1 1 0 0 1 1 matrix. Okay, and yeah, this is same as our spoiler. Okay, and you can compute AX, and you see that it's exactly x1 plus x2 and x2 plus x3. Okay, and yeah, so this example is a bit of a trivial because well, it's pretty obvious to see how to write this x1 plus x2 and x2 plus x3 as a matrix. And we can have less trivial examples. So let's say we do our linear transformation is now not getting this algebraic form. We just say we rotate by some angle theta. Okay, so yeah, so if our linear transformation is we rotate rotate the vector in R2 by some angle theta in counterclockwise, then how we find is a matrix representation. Okay, and geometrically is like this. You have whatever vector, and you have a vector, and you will rotate by angle theta. Okay, and well, once again we go by the definition of RA. We want to see the mapping of standard basis elements under A. So we want to see mapping of this 1 0 vector by A and the mapping of this 0 1 vector by A. And well, the 1 0 vector will get rotated by angle theta, and it becomes this vector here. And so we now need to do some trigonometry, and this vector will have a coordinate cosine theta and sine theta. And similarly, you do rotate this vector 0 1 by angle theta, and now trigonometry will say this length is cosine theta, this length is sine theta, but it's in negative direction. So actually you have the minus sine theta and the cosine theta vector. Okay, and yeah, so we do some trigonometry. We see that the standard basis element get rotated to cosine theta, sine theta, and minus sine theta, cosine theta, and we write it as into a matrix. Then we see our A is cosine theta, sine theta, and minus sine theta, sine theta, cosine theta matrix. Okay. So this is the standard representation of rotation by angle theta. And yeah, this is actually a quite important matrix to remember. It's very nice because well, in a lot of application you want to do rotation by angle theta, and now you know the rotation by theta matrix. I guess you probably also learned this in high school. Here is another derivation of the matrix of rotation. Okay, so any vector x will get rotated by angle theta. Okay, and I think we run out of time here, and we can stop with this question here. So far we talked about how to find the or representation of linear mapping in of the mapping from between Rn and Rm. And if we have even more abstract vector spaces, so if you have a mapping between just some general n-dimensional vector space V to m-dimensional vector space W, then how do we find the matrix representation of our linear transformation? And yeah, that's something we'll do on next Monday. Okay. And yeah, so we can stop class now. Okay. Yeah, so see you next Monday.